be able to see it. So we're going to post this on the ISEE website. They have, and Doreen connected me to the person who's in charge. Our Eastern Mediterranean chapter is still small. We have about 30 members, and we're kind of expanding. So the webinars are part of this capacity building, so that our members who are public health professionals, some are not epidemiologists, other are epidemiologists, general epidemiologists, so that they kind of have a feel of what are the environmental aspects of epidemiology that are most relevant. So we wanted to start with you, and let me introduce you for the sake of our audience. So ALISTAIR Woodward is a professor at the University of Auckland in New Zealand. He's professor of epidemiology and population health. He was the dean of the school and chair, and has been chair of the department there. He is one of the well-known epidemiologists in New Zealand and globally. And I had the honor of being his student as a PhD student. So I learned a lot from him, and I give him a lot of credit to the epidemiology I know. So he's also the ISE council member who is assigned to our chapter. So that's why it was appropriate to start with him giving us this. So each council member is kind of overseeing or assigned to a chapter to take care of the chapter and their needs. And I have been in contact always with ALISTAIR about our chapter. So without any further delay, I'd like to give the floor to ALISTAIR, and then we can open it for questions at the end. If there are comments, feel free to send it through the chat box, and I'll look at them and then raise it to ALISTAIR when needed. Okay, ALISTAIR. So,
well, look, thank you very much, Wael. I'm looking forward to this. Thank you for inviting me to give the first of these webinars. Let me just share my screen.
Mm-hmm.
So, so this is a sort of a personal account of environmental epidemiology and air pollution. I wouldn't claim it as being an authoritative history or a full account of all the ways that epidemiology has been used to understand this problem, but I hope it'll give you a taste of the ways in which environmental epidemiology help us understand this very important problem and look for ways of controlling it. I've given my details here, including my email address, and if any of you want to follow up with me afterwards directly, then please email me. Now, just as a personal history, this is the picture outside my hotel in Beijing in January 2013. It was at a time when air pollution in China, in North China, was at its worst. And on this particular day, as you can see, it really was very difficult to see from one side of the road to the other. And the particulate levels and levels of other pollutions were extremely high. And of course, China exemplifies just what a major problem air pollution can be. In the early 2010s, when pollution was like this, you know, it's estimated that outdoor air pollution was causing about 1 million or 1.2 million premature deaths a year. And a very large number of healthy years of life lost. The other interesting thing about this as a problem is that it tends not to just be a local problem, but also a regional one. So I went from Beijing to South Korea to talk to people there, colleagues who are working in environmental epidemiology, and they were working on this issue of air pollution and had very clever ways of tracking the source of the pollutants that they were seeing in South Korea. And they told me that the pollution in Seoul, a large quantity of it, maybe a half to a third, was in fact coming across the border from China and also from Russia, from South Korea. So this is an environmental health problem that doesn't recognize borders, that has caused an enormous amount of ill health in the past. If we just look at the global picture, this is a map based on satellite readings, so that it's possible from satellites to get a sense of the amount of pollution in the atmosphere. This is from all sources. And you can see that this scale references the WHO ambient air quality guideline, so that all the areas in green fall within the guideline, but otherwise the air quality is judged to be inferior to the WHO guideline. And you can see it is widespread. And as far as the Eastern Mediterranean region goes, you can see on the map that the most countries in the region, by this particular measure, do experience air quality that is less than satisfactory, certainly according to the guideline. Now, you might notice that large, relatively unpopulated areas of the world are coloured in this map. And that's true for Australia. If you look at Australia, those areas coloured yellow, I can tell you, have got very few people in them. So this includes dust and sand, as well as pollutants that are man-made. That, because of course the satellite is blind to the cause of the poor air quality, but it records it nevertheless. And so that explains the picture that you see across Africa and certainly in Australia. What I want to do in the next half hour is cover these points here. Firstly, to give you a sense of the importance of time scale, the question of dose response and guidelines is really important. What sort of advice should we give about air quality? I've just shown you the WHO air quality guideline. Where does that come from? Well, I can tell you it comes from epidemiology. So each of these dot points, in a way, is, to me, indicating the value of epidemiology in trying to understand this particular problem. I want to talk about the rise of indoor air pollution, and whale you feature in this part of the lecture. I think epidemiology has been very helpful, not just in describing the problem, but at looking at the effectiveness of interventions. So I want to touch on that. And then lastly, I want to talk about air pollution at the very largest scale, air pollution in relationship to planetary health, and reflect on some of the work that's underway at the moment concerned with climate change. Well, this is where many histories of air pollution, of course, begin. The Great London Fog in December 1952, and maybe many of you have seen this picture or a picture like it before. It's the 1950s equivalent of the view outside my hotel in Beijing, but much worse, in fact. This man here who's standing in front of the bus, in fact, had to walk ahead of the bus because the bus driver had no way of seeing what was in front of his nose. He needed to be guided. It was an incident in December, in the winter of 1952, when air pollution in London reached catastrophic levels, largely as a consequence of coal that was burnt for home heating at that time. Now, what was the contribution of epidemiology? Well, very simple epidemiology demonstrated that there was this acute effect, both in terms of mortality and in terms of morbidity. So this is just a time series graph showing the number of deaths in Greater London and also the levels of sulfur dioxide, which was the way that air quality was measured at that time. That was, they also collected some information on black carbon, but not in the form that we would report it these days. And you can see that the spike in sulfur dioxide levels, that was when the great London fog descended on the city, coincides with the spike in weekly mortality. The axis across there on the left-hand side. You know, it was unambiguous. It was 2.5 times greater. Very interesting, the level of mortality remained high for about 3 months after the acute air pollution episode. And that tells us that this wasn't simply a case of bringing forward deaths that would have occurred otherwise within the next week or so. This was causing deaths that would otherwise not have occurred, at least not for some time. And it's estimated that about 13,000 deaths over and above what one would expect for this period resulted as a consequence of this great London fog. So this is an illustration of how epidemiology can give us a good sense of the effects of acute exposure. But of course, that's only telling us part of the picture, because we're interested also in what happens to populations which are exposed long-term to high levels of pollutants in the air. And this requires a different kind of a study. The best way of getting at the question of the effects of long-term exposure to air pollution come from cohort studies. So that's where you recruit a group of individuals, follow them over time, have measure of their exposures, and track what happens to outcomes. In this case, all-cause mortality. This is a study that we carried out in New Zealand. So it was a study based on the census. We have a national census, which records a lot of information about every individual in the country, including where they're living. And we estimated their exposures to outdoor air pollutants based on their place of residence using atmospheric monitoring data that are collected by our weather office. Then we were able to link these people to death records and cancer records and hospitalization records over a succeeding 5-year period. And so it was possible to look at mortality rates in relationship to their exposure, adjusting for many other things that may be important, which we were able to do using the information from the census. And the graph shows with increasing levels of PM10, that's particulate matter less than 10 microns in diameter, the odds of dying, estimate of the relative risk of dying during that period from any cause increased. And the different colored bars are different models which adjust in different ways for a variety of confounding factors. But the overall pattern is an increase in mortality of the order of about 10% increase in mortality for every 10 micrograms per cubic meter increase in air pollution. Now, remember, this is long term. So we're talking about areas in New Zealand where we generally have quite good air quality, but there is variation. People who lived in more polluted areas had higher mortality rates. And the effect was, as I said, roughly 10% increase in deaths for a 10 microgram increment. And in the fainter script there, I'm showing you the same statistic based on short-term exposures. It's a 1% increase in deaths for a 10 microgram per cubic meter increment short-term. Now, the reason for the much greater, stronger effect of long-term exposures is an interesting issue, but at simple level, it probably reflects the fact that cumulative exposures are more significant than single or one-off exposures.
Alistair, there is a question about this figure from Rowan asking what are the confounders that basically made these models change?
Good question. So the confounders were other factors that were associated with living in a polluted area, a relatively polluted area, that had independently had an effect on mortality. And the simplest and strongest of those was socioeconomic status. So the areas with the higher pollution tended to be areas where poorer people lived, and we know that low income and social disadvantage is associated with higher mortality. So that was the strongest of the confounders that we had to take into account. We did also have information on smoking habits and age. You know, older populations obviously will have higher mortality rates, but it was mainly the socioeconomic status of the area that was important. So I mentioned this question of what constitutes a safe level or a desirable level of air quality. That's a really important question for policymakers. And the way that we're able to approach this as epidemiologists is to look at the dose response or exposure response relationship, where we've got information on outcomes. In this case, it's mortality, increase in all-cause mortality, in relationship to exposure. This is short-term exposure, daily or weekly particulate air pollution, and it shows 4 panels, and each panel comes from a different study, but each of them shows the same pattern, which is that the relationship between increasing exposure and increasing mortality is roughly linear. And it shows no sign of a safe lower limit. That's not to say there isn't a safe lower limit, of course, but it's just that it's not evident in the studies that have been carried out to date. So the question of how to choose a guideline or a recommended limit or level, warning level for air quality is a challenging one. The WHO guidelines are framed in this way. You can see on the left of the slide, the lowest levels at which mortality has been shown to increase with more than 95% confidence. So as you get towards the lower limit, then it becomes more difficult. We have less information. There may be greater variability, more uncertainties associated with the weaker effect at much lower levels of pollution. And so it's a practical way of approaching it. The guideline there is marked with the red line. So that's the 20 micrograms per cubic meter, short-term exposure to PM10. I've been giving you examples of air pollution that occurs outdoors. And that indeed is, you know, where the investigations of air quality and its effect on health began. But it became apparent to many people that, of course, similar issues might arise indoors. And indeed, since most people spend most of their time indoors, it could be a significant exposure. An example of this is exposure to tobacco smoke, so-called secondhand tobacco smoke. And this mainly occurs indoors, occurred indoors. So there was question whether the if adverse effects of being exposed to tobacco smoke that we know apply to active smokers might also apply to so-called passive smokers. And there were studies beginning in the early 1980s that looked particularly at lung cancer amongst women who had never smoked, but were married to men who did smoke. So that was obviously a source of exposure in the home, particularly at that time in the early 1980s. First study published in 1981 by a Japanese epidemiologist, Hirayama. And what I'm showing you here is cumulative meta-analysis. So this is combining the results of studies of a similar kind that have been undertaken, looking at this question of the relative risk of cancer amongst women married, never smoking women married to smokers compared with the risk amongst never smoking women married to never smoking men. And you can see over the period of roughly 20 years, there were a large number of studies published, combined in this meta-analysis, and they show that the increase in risk is of the order of 30%. And of course, the confidence intervals around that estimate have shrunk, have reduced over time as the evidence is accumulated. So a very interesting example of using epidemiology to study indoor air pollution, pointing pretty squarely at this hazard of passive smoking, which when it was first suggested as a possibility, I must admit, aroused a good deal of skepticism. But it was epidemiology that determined that this was indeed a real problem. Now, this is where Whale comes into the story, because of course, Whale and I worked on this issue of passive smoking in the late 1990s, and Whale was particularly interested in this question of how we measure exposure. And I think this is worth reflecting on because it is an aspect to environmental epidemiology that I think has been quite important in terms of giving us greater confidence in the findings and the results that we've observed. And a good deal of the information, of course, in our studies comes from questionnaires. So people were asked, you know, do you smoke? Yes, no. Does your husband smoke? Yes, no. And that was the basis of the Hirayama study. And people said, well, that's open to error. You know, there might be systematic errors where people are less likely to give the correct answer in some circumstances. It may just be random error. You know, people are just not very good at filling in questionnaires. So to be able to use alternative complementary measures of exposure, that's been an important addition to environmental epidemiology. And Whale investigated the use of hair nicotine. So you take samples of hair, people's consent, of course, and look for levels of nicotine in the hair. And this gives us an integrated measure of exposure to secondhand smoke. Or, of course, if you've got people who are active smokers, it's a reflection of the amount of nicotine that they've taken in from smoking cigarettes directly. And this particular graph comes from a paper looking at hair nicotine in bar and restaurant staff in New Zealand at a time when some restaurants had restrictions on smoking, but not all. So you can see on the far right, here nicotine levels amongst people who were active smokers. Then the levels amongst workers who didn't smoke themselves, but worked in restaurants and bars that had no restrictions on smoking. People working in facilities where half the space indoors was smoke-free, and then a smaller number, but we had a number of bars and restaurants where smoking was totally prohibited. And you can see the very strong relationship between the environment, or in particularly the presence of restrictions on smoking, and the levels of nicotine in the hair of people who were working in those at those places. So this provided very strong support for the questionnaire-based information that had been obtained on levels of on exposures, and provided a lot of support actually for the subsequent comprehensive smoke-free environments legislation that was passed in New Zealand in 2004. Now, I'm coming now to the point about interventions, and I think this is an interesting part of the story, that epidemiology has been used to both make good use of so-called natural experiments, and also to study in the setting of trials, formal intervention studies, the impact of actions taken to reduce pollution, and looking to see what the health benefits might be. My example of a natural experiment is the 2008 Beijing Olympics, where you might remember, many of you, that the Chinese government brought in a whole lot of changes immediately before the Olympics, in order to ensure that the air quality was acceptable during the Olympic Games. You remember this was a period when air pollution was a huge issue in northern China. So the government felt that it needed to act. And so they introduced severe restrictions on traffic. They essentially halved the activity of power plants, particularly those that were powered by coal. And then what were the consequences? This was the interesting bit where epidemiologists got involved to look at just what might be, if there were any discernible health benefits of this change. And I'm particularly keen on the taxi cab studies. I think these were so clever. So you can see there the measures of PM 2.5, so that's small particles, measurements taken inside taxi cabs in Beijing before the games, during the games, and then after, when the restrictions on emissions were reduced. And you can see that levels were more than halved during the games. What about health consequences? Well, we know that one of the most sensitive physiological responses to particulate pollution is a reduction in heart rate variability. Very interesting. I don't fully understand the physiology of this, but it's well known as a feature of exposure to particulate pollution. And you can see that before the games took place, measures of the ECGs taken of taxi drivers showed that they had less variability in their heart rate than one would expect to see. That changed when the games took place, moved to a more normal state, and then reverted afterwards. There were other studies done looking, for example, at asthma admissions. I'm showing you there, and modeling studies estimating what the effects might be on cancer risk. So here's an example of a natural experiment, epidemiologists involved in trying to understand what the effects might be in order to learn something about the efficacy of clean air regulations and interventions. Here's an example of a formal trial in the indoor air pollution area carried out by Kirk Smith and colleagues, looking at the effect of replacing traditional open fires used for cooking, as you can see on the left, with wood stoves that had chimneys, so that the pollution indoors was greatly reduced. Looking at the effects on acute lower respiratory illnesses, this shows the relative risk associated with being in the intervention group, reduction in pneumonia, although that wasn't statistically significant, but clear impact, a stronger impact on the frequency of severe lower respiratory illness, as reported by the participants or as reported by, diagnosed and reported by doctors. So a formal trial looking at indoor air pollution, this coming from biomass cooking, demonstrating that improved wood stoves did indeed lead to both an improvement in air quality and health gain. I thought I'd mention this one as well, just because masks are a bit in the in the news at the moment with COVID, of course. I thought this was a rather interesting study, a rather clever one, done looking at the effects of wearing masks, simple face masks, on the health effects of exposure to particulate air pollution. And this is outdoors. And so it involved working with healthy young pedestrians in Beijing, a crossover study. So it was the same individuals who were studied, observed with and without the mask, showing that the use of a mask of this kind, and I emphasize it's not a simple surgical mask, a paper mask, it's a proper particulate respirator, that those masks obstructed, blocked the adverse effects of air pollution on blood pressure and heart rate variability. So a study to show that an intervention at the personal level did bring benefits, did offer some protection. And finally, I said that I wanted to just talk a little bit about air pollution and epidemiology and climate change. This is very much on my mind because I'm at the moment working with the IPCC, the Intergovernmental Panel on Climate Change, on the 6th assessment report. The IPCC puts out major summaries every 5, 6, 7 years, state of knowledge relating to climate change. And I'm helping write the chapter on our region. Now, one of the most significant events that occurred recently in the last 5 years in Australia and New Zealand and our corner of the Pacific are the bushfires that occurred in Australia in the last summer, our last southern summer. So these were started in about November 2019, roughly 12 months ago, and continued all the way through until late February, early March. And what was significant about these fires is that they were hotter, bigger, and longer lasting than bushfires in Australia previously. This is a picture of one of the fires in the Blue Mountains outside Sydney, just to give you a sense of the scale and intensity of the fires. Now, as a consequence of these being such large fires and burning for so long and burning so hot, there was a huge amount of smoke generated. And it's estimated that 80% of Australians were exposed to this smoke. Now, that's remarkable. Of course, the densest, most densely populated part of Australia is the southeast, and this is where the fires occurred. Nevertheless, the smoke did cover a good part of the country for a prolonged period, including some of the very populated, most populated areas. So I'm just giving you there the example of Sydney, Australia's largest city. Through November and December, 1 day in 3, the PM 2.5 levels exceeded WHO guidelines. And this is quite extraordinary. This is unprecedented. So here we have an extraordinary event, and it bears the fingerprints of climate change. Formal attribution studies are still being carried out, but it's estimated that the odds of this happening under climate change are, you know, it's a sort of 40% increase in likelihood of this occurring over and above what one would expect to see just due to natural climatic conditions. Long drought, extreme heat, high wind, essentially the genesis of these fires. So the question of what the consequences for health were, this is a story that's just emerging, really. What I'm showing you here are the estimated numbers of premature deaths, admissions to hospital for a variety of disorders, and the associated economic costs, healthcare costs, associated with the wildfire season, the bushfires that I've just told you about. You can see roughly 430 premature deaths estimated to result from the exposure to smoke, and large numbers of hospital admissions for either cardiovascular problems or respiratory diseases. And the total cost, healthcare cost, is of the order of $2 billion. Then, to give you some sense of how this is calculated, we could talk about that later if you like, but it's essentially looking at the number of people exposed, trying to estimate what you would think that you expect the incidence rate to be in the absence of the fires, the dose-response relationship, and the exposure level to PM10. All those things put together allow you to calculate the number of outcomes that you believe can be attributed to this particular exposure. So unprecedented costs of smoke-related PM 2.5 from the mega fires. This is important because there is a lively discussion about what to do about climate change. This is particularly so in Australia, where the costs of changing the economy to move away from fossil fuel intensive industries is substantial. And so policymakers ask reasonably enough, what's likely to be the cost or impact if we don't act? And so this information is extremely helpful for us at the IPCC, where we lay out the options for policymakers and the consequences of taking different policy paths. You might also notice, just on the left-hand side there, that the number of deaths from the bushfires that occurred from burns and injury was much smaller than the number associated with poor air quality from being exposed to the bushfire smoke. But it's that number, 33 deaths, that of course were in the headlines at the time that the fires occurred. So I'm happy to answer any questions that you might have. This is the ground that I aim to cover, and I hope I've given you some insights, some ideas, some thoughts, and maybe some questions about these topics. I've also got 3 references that I'd suggest if you want to follow up on these topics. The first paper is a very interesting and nicely written paper describing the contribution of epidemiology to understanding the effects of fine particulate air pollution. The second is a paper written by Kirk Smith and colleague. This is in early 2000s, but I've suggested it because it lays out the scale of the problem of indoor air pollution and the health consequences that result from those exposures if no action is taken. And then the third paper, the most recent one, is a paper commissioned from Andy Haynes by the International Journal of Epidemiology, in which we invited Andy to reflect on the so-called Anthropocene epoch. So this is the era that we've arrived at, where human activity is changing the shape of the planet. Climate change is one example of those changes, and we asked him to reflect on what this means for epidemiologists.
Thank you, Alistair, for this very nice range of topics that range from indoor air pollution to air pollution outdoors, as well as climate change. I want to ask our members, since we have few members, if they want to open the microphone, introduce briefly themselves, and ask the questions. So maybe we start with those who have put some questions in the chat. Go ahead, and if you feel free to put the video on or not, but let's try and do that. Who wants to go first? Rowan, do you want to go first?
Yeah, sure. Hi, and thank you very much, Professor Woodward, for this very insightful presentation of first-hand epidemiology, if you may. I actually have 2 questions. The first is, are there any plans for natural experiments of air pollution, such as the one you presented?
That's totally normal, don't worry.
I'm really sorry, it's early morning here, yes. And I'm still at the house. Yeah.
Go ahead.
So,
I think you're muted. So I'm going to read the question for Rowan. I think. So are there any plans for natural experiments for air pollution pre or during post-COVID-19 pandemic? What type of studies can take advantage of such situation to bring new regulations? And second, what evidence of particulate respirators and face masks helping protecting against air pollution can be presented as a way to motivate people to wear masks during the pandemic?
Thank you. Those are 2 good questions. COVID is on our mind, everybody's mind at the moment. Yes, one of the obvious features of the COVID pandemic has been that many countries have gone through a period of lockdown or severely restricted mobility. And a consequence of that, of course, is that that air quality has improved, even if it's only temporarily. And there are a number of studies, some published already, others that are on the way to being published, that have looked at the improvements in air quality and at the health consequences, either from direct observation, where it's possible to look at things like hospital admissions or mortality, or by modeling. What would one expect to see based on what we know about those dose response curves as a consequence of the reduction in pollutant levels associated with COVID lockdown? The effects are substantial. You know, the reductions in pollution have been maybe of a similar order to those seen in Beijing during the Olympics, halving or maybe a bit more than a halving of pollutant levels. And one would certainly expect to see substantial improvements in health. It's a little difficult. There are other things that were happening at the same time. Here in New Zealand, you know, we know that people stopped going to hospitals, even perhaps when they should have, because they were rather anxious about COVID. And so that partly explains, you know, the reduction in hospital visits. And there was a reduction in mortality overall associated with lockdown, which probably had a rather complicated explanation. But you're right, you know, this is a good example of an actual experiment, and certainly people have taken the opportunity to look at using this period to get better understanding of the effects of environmental change. Your second question about masks, I'm not an expert on masks and COVID. I appreciate that it's a topic that you know, that people have debate, but the logic is similar, I expect, and the observation from the particulate pollution story is that you really need to wear a high-grade mask to get reliable protection. So simply wearing a bandana or a paper mask makes relatively little difference to the particulate load that you inhale. The kind of respirator that I showed in the slide, you know, is one that is very snugly fitting and has a high-grade filter in it. And those kinds of masks are not terribly comfortable to wear for long periods, actually. And I think that's an issue that's been true also with COVID, certainly in the healthcare setting, that providing masks for healthcare workers that will reliably block the transmission of the COVID virus are expensive and are difficult to wear for long periods of time.
And Alistair, there's another comparable question from Asad Nafis saying, do we have evidence that simple surgical masks can reduce particulate matter? And I think you probably already answered it.
Yes, I think they do make a difference, but not a great difference. Mm-hmm. For all the obvious reasons. You know, they tend not to be close fitting, and people don't necessarily wear them as they need to be worn, and the filtration is limited.
Right. And Dr. Ahmed raised your hand. Do you have a question? Please go ahead.
Yes, thank you. Thank you, Prof. Wall. Hello, Prof. Alistair. Thank you for your presentation. Hello. Can I ask a question?
Yes, go ahead.
Are the outdoor pollutant devices same used in indoor pollution devices? I mean, in research aspect, we learned and we know that the outdoor pollutant devices is so expensive. I mean, in Iraq, in our country, even our ministries doesn't have it. So if a researcher wants to do an indoor air pollution research. Any device, any simple device, cheap, practical that can be used, or should we use the biomarkers like Prof. Wild did in New Zealand through hair, urine, etc.? Thank you.
There are quite a variety of air quality monitoring devices that you can use, and some of them are relatively simple. So I would hope that, you know, in your country that you might be able to get access to particle counters, to simple monitoring devices that you can use actually for various pollutants, and they can be used both indoors and outdoors. The biomarkers are more difficult. That requires, you know, laboratory support and backup, and is very specific to particular pollutants like secondhand smoke. Wale, would you comment on availability of monitoring equipment?
Yes, we had a workshop with the World Health Organization Regional Office Center for Environmental Health Action in Jordan, Amman, exactly about a year or so ago. And they had an expert, actually a Jordanian expert, who is an air pollution monitoring expert who has, you know, he's a physicist, so he has 2 or 3 monitors that he has worked on and provided. So I think these they demonstrated 2 or 3. I forgot the names of them, but these are the ones that are recommended. They're not cheap. I recall the prices were, you know, more than 1,000, at least the cheapest one. So, but these ones need to probably be purchased by a university or the Ministry of Health as part of a study, and that's possible. It just needs the funds probably to get them. There was a question. There was a question from Kenza. Kenza, do you want to speak, or do you want me just to read it?
Good morning. I will speak. So good morning, everyone from where I am. Hello, Dr. Alistair. Thank you so much for the presentation. So I'm wondering, in fact, if there is any researches about the future impacts of bushfires on climate and air pollution, mainly. Were there any efforts with regards to modeling these future impacts and how our climate will be affected in like 10 years or 20 years in the future, and likewise for air pollution? So this is my first question. My second question is there any clarity about how air pollution and climate impact exposure to COVID? Thank you.
Oh, thank you. Two thoughtful questions. The modeling question. Bushfire risk is quite difficult to model. You know, temperature is relatively straightforward given the sort of physics of the atmosphere and what we know quite full well happens as a consequence of loading the atmosphere with greenhouse gases. Fires are driven, fire risk is partly a product of temperatures, but it also relates very much to moisture, to rainfall, to changes in seasonal patterns of rain and the intensity of rain. And that is more difficult to model. So certainly there are projections for the fire season in Australia, in North America, in other parts of the world, in the expectation that the season will lengthen, start earlier, finish later, and that the risk of severe fires will increase just as a consequence of higher temperatures. But whether that translates into fire occurrence, of course, is a far more difficult step in terms of estimating just what the risk for any particular location of fire might be. And then I think you were referring also to the question of what the health impacts of those events, might be. And again, that has quite a deal of uncertainty associated with it, depending on, do people build back in fire-prone areas? How effective are emergency services? And all those considerations. So that certainly the IPCC report will be commenting on the likely effects of climate change on fire risk. Might not have much to say about just what the health impacts are likely to be, because we perhaps don't have as much information in that respect. Your second question, am I right? You asked about air quality and COVID risk. Was that the question?
Yes, air quality, climate, and exposure to COVID. Exactly.
Okay. There is quite a lot known about the interaction of climate and air quality. So we know that very high temperatures carry health risk. We know that exposure to air pollution carries health risk. If you put the two together, we know that you get a multiplication, so that there is a synergy, there is interaction between those two exposures. If they come together at the same time, then the health consequences are greater than would occur if they were in isolation. The effect on COVID, I don't think, is so well understood. It's interesting, isn't it? Is there a strong seasonal pattern with COVID? It looks as though that might be happening with the resurgence of the virus in the Northern Hemisphere as they begin their winter. Is that temperature related? There's some reason to believe it might be, in that virus survival is greater at lower temperatures. And also possibly there's more crowding when people are indoors during the winter. There's some suggestion that areas with poor air quality are also prone to more severe COVID illness. But it's perhaps too early, I think, to be absolutely confident about that, because goodness, the disease is novel and we're still struggling to understand everything that's involved in its etiology.
Yes, I want to add that there are a few studies still appearing that do show there is an association with higher air pollution and COVID-19. But of course, I think these are, as you suggest, are a bit too early to make the correlation. One of the reasons I've heard is that in northern Italy, the COVID-19 hit the worst, the nation, because that's the most polluted area of Italy. There's the factories and so on in Turin and all these areas. And that was one of the explanations, that the air pollution exacerbated the severity. And I also want to comment on the wildfires, because here in California we have a lot of these wildfires or bushfires, as they're called in Australia. And the main challenge in terms of its relationship to health impact is how to quantify the exposure in terms of these. I think we will see studies soon, because now we are seeing the air pollution is so bad, just like in Australia, that we can see there will be an impact. But long term, I think Kenza was asking, is this going to have a long term through modeling prediction of how this will contribute to climate change? That's a very, I think, very challenging model. I don't know if anybody has tried to model that.
I think there has been work done looking at the effect of particulate pollution and climate, and on the whole, particulate pollution in the upper atmosphere has a cooling effect. You know, it tends to reflect incoming solar radiation, and so there's a suggestion that the high levels of pollution in places like China, you know, in the early 2000s, may have masked the effect of climate change, you know, may have contributed to what looked like a sort of hiatus in global warming. Temperatures sort of flattened out a little bit. And as the air quality has improved, perversely, air quality improved, then climate change has returned, you know, in full force. So the bushfires certainly have contributed to the particulate load in the upper atmosphere, and to some extent may be mitigating, you know, the early effects of climate change by cooling the atmosphere, cooling the earth overall.
Yeah, I recall when I was growing up in Iraq, we would have these seasonal desert storms. So the whole atmosphere becomes reddish, red to yellow, because of the dust. But usually the days after it becomes cool. You know, we get a relief from the extreme heat, which is typical in that region. So that, you know, that is an actual observation, personal observation. Well, I think we were a little bit over time, but I really want to thank you on behalf of our chapter, on behalf of my co-chair, Nargis Kanjani, also for this very informative webinar that we started this series, and we'll hopefully post these for others to see and send it a link so that they can benefit from it. But thank you again, Alistair, for your contribution, and thank you for those who made it despite all the confusion about the daylight saving and whatnot. So so we'll be in touch again with everyone else in the chapter. Thank you very much.
Very good. Thank you, and good night.
Thank you. Thanks, Alistair. Bye.